All right, welcome everyone. It's my great pleasure to welcome Marie Gueguen today, who is a postdoc at the University of Pittsburgh. He works at the Center for the Philosophy of Science there. Marie received quite recently her PhD at the University of Western Ontario, where she worked under the supervision of Chris Mink. And so she specializes mainly on the philosophy of cosmology and the philosophy of computer simulations. So thank you very much, Marie, for accepting our invitation. Please take it over.
So I'd like to start by thanking. Should I close the door?
Yes.
So thank you very much first to Baptiste Levillon and Christian Bushfish for inviting me. It's a great pleasure to share my work with you today. And I apologize for those of you who've already heard some part of the talks. Hopefully it's going to help refresh your memories to understand the most technical part. The more technical part in the second part of the talk. So what I want to talk about today is the role of simulations in astrophysics and motivate the need for new tools to assess their reliability. So the first part of the talk will be a negative one in the sense that I'm criticizing existing method for assessing their reliability. But what I'm really interested in is motivating a new methodology that I think could actually fulfill this task and do better than current methodologies. So I'll start by describing the role of simulations and explaining why they're so essential today to the practice of astrophysicists. So what you see on this big picture, it's actually a simulation from the Eagle group, are the largest known structure of the universe, cosmic filaments and voids. The scale of this structure is about hundreds of megaparsec. These filaments are made out of clusters of galaxies, which are themselves made out of galaxies. Galaxies form in dark matter halos. And within galaxies, you have a lot of processes going on that affect the distribution of matter, both in galaxies, baryonic physics, and in the dark matter halos, the dark matter physics. These processes, among others, include supernovae feedback, like when stars are exploding at the end of their life, black holes growing and generating jets and winds that affect the interstellar medium, the gas cooling, the ultraviolet background. So there's a lot of processes happening within galaxy that are happening at a scale below the parsec scale. So there's a lot of dynamic process, an enormous dynamic range of processes to take into account. And their non-linearity, their variety, and their interplay makes it impossible to have an analytic solution to describe what's going on and to have an answer to the question, what does the standard cosmological model imply for structure formation? So simulations are absolutely essential to understand how structures form in the universe. They play a variety of roles. I won't spend too much time on this variety during this talk, but they're not only useful to extract prediction from competing dark matter proposals, but they're also useful for supplementing observations when these observations are too sparse, and to design and implement observational surveys. So they're everywhere and really ubiquitous in the practice of astrophysics. When you talk about simulation, you can refer to many different things. Today, I'm going to focus on dark matter simulation because the problem I want to point at in simulation already happened at that level. You don't need to consider baryonic physics to meet your first problem when it comes to assessing the reliability of simulation. So I'll be focusing on dark matter only large simulation and on dark matter zoom-in simulation. But you have different kinds of simulation. So this is a large volume simulation including only dark matter with aims to reproduce the cosmic filaments we've seen earlier. This is including baryonic physics as a way to make the simulation more realistic. And this is a zoom-in simulation that actually target one of these halos you see here and resimulate it at higher resolution to better understanding the processes leading to galaxy formation. Among the ingredients of simulation I'll be talking about today, you have initial conditions, so the size of the box you're simulating, the number of particles that your simulation will include and the way these particles are distributed over the volume. And you also have the gravity solver. So the way you're calculating the forces, gravitational forces, between dark matter particles. You have a variety of ways to do that. Either you can sum up overall the contribution of all individual particles. So you can impose a mesh on the volume you're simulating and calculate the density field for every node of the mesh. Or you can group particles together and build a tree code. And in this case, you're not going to take into account individual contribution of each particle, but group them together and replace them by a single multiple force. That's basically all you need to run a dark matter only simulation. Initial condition, Newtonian physics, gravity solver. And if you want to run a simulation more realistic, a hydrodynamic solution, you will need to implement some parameters describing the physics happening, the baryonic physics happening at below the scale of the simulation. But I won't need to talk about subgrid physics for my purpose today, so I'll skip the subgrid physics, but we can talk about it later if you'd like. I want to insist on one common assumption that all codes have to make in order to run a simulation. It's the fact that dark matter needs to be discretized. Dark matter should be modeled as a continuous system, as a fluid, but given the limits on the resolution, you have to substitute to dark matter fewer but more massive particles so that you can average the density of real system. So that's one assumption that can create discreteness-driven artifacts in simulation that you really need to be careful with. And not only you can create discreteness-driven artifacts, but the particles you're substituting not only are discrete, but they're also extremely heavy. They are of the order of millions of solar masses. So for such particles, you will have a physical acceleration that do not have any counterpart in a real astrophysical system, since dark matter particles have a very tiny mass and so behave collisionlessly. So not only you will have discreteness-driven artifacts, but you'll have artificial collisionality that is usually taken care of through force softening, which is a trick that you're adding to the simulation, a departure from Newtonian physics, that smooths the gravitational potential within a given radius. Okay, so the simulation based on the cold dark matter model are really good at reproducing the large-scale structure that we know. But they're equally good as warm dark matter model or self-interacting dark matter model. So if you want to discriminate between these rival dark matter models, you need to look at what's happening at small scale. And what's happening at small scale is not good for the cold dark matter problem. You have a bunch of controversies. I think right now the list is 5 or 6 of them. You have an excellent review in Del Popolo and Deliu and in Boylan and Bullock and Boylan-Koechlin if you want to look all of them. I'll be focusing on 2 specific problems today, the missing satellite problem and the cusp core problem. So the first one, the cusp core problem, is about the density profile, the distribution of matter in dark matter halos. So prediction based on cold dark matter simulation, so prediction extracted from cold dark matter based simulation, predict a density profile that is cuspy at the center, while observation favor a more flatter, a more uniform density distribution. Not only it contradicts the universality of the density profile offered by Navarro Frank White, but the problem is that observation favor a uniform, flatter profile, especially for dwarf galaxies and for low surface brightness galaxies. And those galaxies are not supposed to contain a lot of baryonic physics, which means that you're not going to solve the problem by being more realistic, adding more baryonic physics or better understanding the baryonic physics. Dwarf galaxies do not contain baryonic physics, or so few that it shouldn't impact the density profile. So this is referred to as a cusp core profile, the cusp core problem. The second problem is the missing satellite problem, and this time it's not about the demographics of the distribution of matter, but about its abundance. In a dark matter halo of the size of the Milky Way, according to cold dark matter-based simulation, you should observe several thousand of subhalos hosting satellite galaxies. And in our current Milky Way, we observe only 59 of them. So there's a lot of substructure predicted in a dark matter halo by the cold dark matter model that we do not observe in a system like the Milky Way. And as I mentioned before, these two problems are really essential in order to discriminate between rival dark matter models, because the abundance and demographics of dark matter substructure are the prime discriminators between different dark matter models. The warm dark matter model, for instance, doesn't suffer from the missing satellite problem, and the self-interacting dark matter model doesn't have a cascade problem. So if you want to favor a model over the other, you will have to address the question like how worried should we be about this controversy about the density profile and the substructure discrepancies. So that's exactly the question. How should we interpret this discrepancy between cold dark matter based simulation and observation? Should we go as far as saying that the cold dark matter model is refuted? Should we make a more humble claim and think that maybe it's the prediction we extracted from the cold dark matter model, the Navarro Frank wide density profile, which is inadequate, and maybe a better density profile could be compatible with the cold dark matter model, but do better in predicting substructure and abundance of dark matter halos? Or we should pause and think that maybe n-body simulation do not faithfully track the logical consequences of the cold dark matter model, and make sure that it is the case before discarding the entire model. And so this is where you need to ask, what are the current tools that are being used in order to assess the reliability of simulation? How do they fare, and can we do better if they do not fare good? So currently the two ways simulation are being assessed are based on robustness analysis. One is an internal form of robustness called convergence studies. It's defined by Orzak and Sober as follows. A numerical prediction of a model is said to be robust if its value does not depend much or at all on variation in the value of the input parameters. So here you're considering robust analysis within one model or code, and you're trying to find robust properties within one code. The direct translation of this in astrophysics is convergence studies. But you also have another form of robustness analysis, this time external form of robustness, where you're looking for robust property across different models. And this time you're cross-checking different codes in order to find robust properties that would not depend on the details of your code. So as I mentioned, both of these forms of robustness analysis have direct translation into astrophysical practice, convergence studies, and code comparison. I put here the title of one of the most famous convergence studies, that of Power et al., where the methodology of convergence study was actually defined as follows. So the search for regions in parameter space where the property under scrutiny, here the circular velocity curves, are independent of the value of the numerical parameters. When it comes to code comparison, the idea is to compare different code and to look for robust property across these codes. And so Kim et al. From the Agora project defined a code comparison in the following way. Our experiment reveals a remarkable level of agreement between different modern simulation tools, despite their code base having evolved largely independently for many years. It's also reassuring that our computational tools are more sensitive to input physics than to intrinsic differences in numerical schemes, and that predictions made by the participating numerical codes are reproducible and likely reliable. If adequately designed in accordance with our proposed common parameters, results of a modern high-resolution galaxy formation simulation are likely robust. So if you find agreement across different codes, given the proper methodology, Kim et al. Are confident that you actually found robust properties that reflect the physics that you try to implement in your model. So let's test these two methods. So I mentioned earlier some argument against convergence study. Here I want to talk more about theoretical consideration that might prevent convergence study to be successful in principle, and also a case study that shows that it fails in practice in detecting artifacts. So I'll focus on discreteness effects and on the way convergence studies and code comparison can actually detect artifacts driven by discreteness effects. So the fact that you have to discretize dark matter might create many kinds of discreteness effects. I'm putting quotes here for kinds because it's not clear how you can disentangle these different contexts, these different kinds of discreteness effects. But you can have collisionality, exchange of energy, and change in momentum of the particle. You can have two-body relaxation that you calculate summing over all two-body scattering process. So when you have a change in the velocity or in the trajectory of particles. Collective relaxation coming from large-scale fluctuation. Or you can have what's called a shot noise or Poisson fluctuation, where the discretization of dark matter will actually create velocity, discreteness-induced velocity fluctuation that will enhance the effect of small-scale fluctuation and that will enhance the collapsing effect. So let's focus first on two-body scattering. So a form of collisionality, the consequences of collisionality. For real system of dark matter, in the limit of small particle masses, for a system of dark matter particles only interacting gravitationally, the particle-particle scattering becomes unimportant and the evolution resembles that of a continuous system. So that's what we should aim at when we run a simulation, a continuous system. As I mentioned earlier, this is not the case. You cannot model a continuous system. This would require an infinite number of particles. So instead, you have a small number of high-mass particles. So do they suffer from artificial two-body scattering effects given their mass? And if so, how would we know? Well, as you can anticipate, convergence studies, that would be the answer of astrophysicists. We can detect artifacts using convergence studies. So the idea is that if we really think that discreteness effects affect the density profile, and that discreteness effect comes from the limited resolution of the simulation, then if the density profile depends on the resolution, increasing the resolution of the simulation should have an impact on the density profile. So in the large n limit, the discreteness effects inherent to n-body simulation should vanish, and convergent tests will tell us how the density profile reacts to an increase in resolution. So if discreteness comes from a limit of resolution, we increase the resolution and we'll see how the density profile reacts, whether it varies or not. If it doesn't vary, it doesn't depend on the resolution and we're safe. That's the reasoning. So let's grant that we can actually run a simulation with a large n limit that will tell you whether such effect vanish. Is this reasoning really able to capture what's happening with discreteness-driven effects? So, in a cold dark matter universe, structure forms bottom-up. So you have first objects forming from a fewer number of particles, and the largest structure will form from the merging of small objects, of the first object. So first object will always contain a few number of particles. So this first object are the most likely to be exposed to discreteness-driven effect and actually severe relaxation effect. So when increasing the resolution, what you're actually doing is to create a context where the first object will have higher physical densities and they will condense out from a denser environment. So they will be even more exposed to discreteness effects. The higher the resolution, the higher the density of this first object, and the more they are exposed to two-body relaxations. Based on this reasoning, Bin and Neighbor in 2002 have been arguing that if you think of objects forming that way and being affected by discreteness-driven effect, then convergence test of the time performed by Gueguen et al. And Clippin would be powerless to expose discreteness effects if this spectra were valid. And Demand et al. Insists that two-body relaxation increases with density, so it's not clear if increasing the resolution can diminish the overall amount of two-body relaxation in a CDM simulation. That is, if testing for convergence by increasing the mass resolution is appropriate. So if relaxation really modified the internal structure of dark matter halos and tend to make the core denser, for instance, as is thought to be the case, how much should we trust the Navarro-Frank-White density profile, and how much should we consider that the Kasparov problem is an actual difficulty for the cold dark matter model? Now, can code comparison help with this problem? I'll go faster on this because I think the problem is clear. There is a large variety of codes, tree codes, particle-particle codes, adaptive matrix refinement codes, but they only differ in the way they calculate the forces between particles. They all discretize the dark matter fluid in the same manner. So if discreteness is a common assumption of any code, common assumption will likely lead to common errors. So it's not by cross-checking codes that you will detect whether they suffer from discreteness effects. So that is all well, but it's theoretical consideration. It's just a theoretical reasoning indicating why convergence study might fail in detecting discreteness effects. But let's apply convergence study to a real case, a really interesting case study that has an interesting history. So for a very long time, it has been known that warm dark matter model-based simulation are suffering from spurious fragmentation. So warm dark matter particles have a thermal velocity that is higher than cold dark matter particles. And because of that, when you have this small scale density fluctuation and seeding the collapsing of dark matter model, in the warm dark matter model, the velocity is such that particles actually wash out the small scale fluctuation. So structure do not form bottom up, it forms like top down, which means that the smaller structure form from the fragmentation of larger structures. So in warm dark matter simulations, they observed low mass halos in simulation that you see in the circles here that are smaller than the cutoff scale in the power spectrum. So the question was whether those halos were artificial, spurious halos, or born from the fragmentation of larger structures. And given what was known about how structure forms in warm dark matter model, the first insight was the second one, that these halos were real halos and that they were born from the fragmentation of higher mass halos. But later, there was a study here. I put a picture by White and Wang because I think it's really telling. But the first study, I think, showing the artificial nature of these halos was by Guts and Sommer-Larsen in 2002. And what they actually showed was that the spacing between low mass halos was the same as the grid that they were using to distribute particles in the simulation. Mm. And so what I mean by the grid is that the halos were spaced in the same, like in the way that was proportional to the mean interparticle distance. So they started using, well, probably it's artificial, right? But it's not a problem. It just depends on the initial conditions and the way we're distributing particles. So if we find another way of distributing particles in our simulation, the problem will be solved. And that was the point of White and Wang study, trying to determine whether that's the case or not, whether if you use different initial conditions, then this problem will disappear or not. And they showed that no, it doesn't. If you modify the initial condition, and they use glass-like condition, I'm not going to go into the details here because it's not needed, but if you use different initial condition, you still have the same problem, and you can still see these, they call that beads on the string halo, that are clearly related to the spacing of the grid. So it became a more worrying problem, because if these spurious halos do not depend on initial conditions, then there's not so many options to understand where they come from. And one of the options, and the most likely option, is that they're due to discreteness-driven effects. That is velocity fluctuation that are induced by the discretization of the density field, and hence the collapse of matter and create these low-mass halos. But if these spurious halos are due to discreteness effects, then there's no reason why they shouldn't affect cold dark matter simulation too. It would be more difficult to detect because in cold dark matter you have small structure forming first, so it would be difficult to disentangle this discreteness-driven velocity fluctuation from small-scale fluctuation corresponding to what's predicted by the model. But there's no reason why such discreteness effect in warm dark matter model should not be present in the cold dark matter model as well. So again, how do we know? And I should point out that there's a well-known problem for cold dark matter simulation that has been pointed by Ludlow and Porciani in 2011. If you're looking at the progenitors, the ancestor of low mass halos in the linear density field, so before the collapse, you don't find them. They didn't identify any progenitors for these low mass halos. It was like, roughly speaking, they pop up after the collapse. So there's really good reason to think that maybe low mass halos in the cold dark matter model, as it's described by simulation, are of spurious nature. What do you do in that case? You run a convergence study to determine whether low mass halos in the cold dark matter model and cold dark matter based simulation actually resist in change in the force softening, because force softening should cancel this velocity-induced fluctuation. So here what you observe is the mass function for warm dark matter model and cold dark matter model. Warm dark matter in blue and cold dark matter in red. So the mass function is giving you, roughly speaking, the number of halos you have for a given mass. And so if really the low mass halos are spurious and due to inadequate force softening, for instance, when varying force softening, you should have an upturn for mass of low halos. So you should observe more low mass halos when you're reducing the force softening. And this is exactly what's happening for warm dark matter. You observe here that the smaller the mass, the higher the number of halos you observe. But people were thinking, well, you don't observe such an upturn for cold dark matter simulation, and you have good convergence rates between different softening. Here you see the prediction of the cold dark matter model based on different value of force softening, and they converge very well. They agree really well with each other. So based on convergence study, we should trust simulation based on cold dark matter model. A problem with this reasoning might be that, well, you have an upturn for warm dark matter simulation, but you also have very good convergence. So does it converge on a real solution, or do you really think these halos in warm dark matter model are artificial or not? Convergence is reached for the warm dark matter model too, so what kind of conclusion should we reach just based on convergence studies? So clearly it's not enough to tell whether cold dark matter model-based simulation are reliable or not. So Power et al. In 2016 pushed the line of reasoning a little further, and they ran a really interesting experiment. And the idea was to run a plane, a one-dimensional system simulation. If it's collisionless and it's one-dimensional, it should remain one-dimensional. So the plane that you're simulating should retain its shape as it winds up. But if it is collisionless, if it is collisional, then the velocity fluctuation induced by these discreteness-driven effects I've been talking about will cause the plane, the sheet, to thicken and to fragment into clumpy structures at later time. So they ran the simulation, and I should indicate that this is a reasoning that is well known since the 70s, and several experiments have been done already with the cold dark matter model of that kind, and they all pointed at collisionality. So here is a result of Power et al. In 2016. So here you see simulation with a increasing force softening, and here it's a redshift equals 0, and this is a little later at redshift equals 4. And what you're observing is that the smaller the force softening is, the thicker the sheet is becoming. And so you do observe collisionality for this system. And you can see that it thickens and then fragments and doesn't retain its shape at all as it winds up. So there is collisionality in the system. And this experiment shows that there is collisionality, but it was not detected by the convergence study. According to the convergence study, you change the force softening and nothing happens. The Hello mass function remains the same. There's many reasons why there's such a difference between these two simulations, and one of them is that if real dark matter halos dominate in the cold dark matter model, then it's not going to affect the mass function, but it doesn't mean it doesn't affect the distribution of matter and the density profile. So this might be one of the explanations of such a difference between the results. And what I find really interesting is the reasoning that led to the Powerdell experiment. They're not trying to reach convergence, they're not trying to test different codes. They're really running what philosophers would call a crucial experiment, a crucial simulation in that case. They're comparing a physical hypothesis to a numerical hypothesis and trying to extract a given prediction for one of them that would not be satisfied by the other. So here the idea is that if the system is collisional, then the one-dimensional system should not remain one-dimensional and it's going to thicken, as we saw. If it is collisionless, then we should not observe such phenomena. Then you run the simulation and you can tell apart these two hypotheses, a physical vs a numerical one. And there's many ways you can do that to detect discreteness-driven effect. I'm just going to mention a few of them. But in 1985, already, Eustachiou and Eastwood, in order to test their code, they were developing 3PM code at that time, and they wanted to test whether their code was collisional or not. And what they did was to run a simulation with two different masses, particles of two different masses. And if the code is collisional, then you should observe mass segregation effect. The heavier particles should sink down and make the core denser. If it is collisionless, then the particles should remain mixed. It's a really simple simulation to run in order to test your codes. But it's not realistic at all. You're not going to reproduce anything realistic by doing that. You're not going to match observations. But it's a really efficient way to test whether your code is collisional or not. And it has nothing to do with convergence. It's really extracting a prediction from a physical hypothesis or a numerical hypothesis, and then design a scenario where you can actually verify whether this prediction is true or not. Binet and Neber and Kneber, I don't know whether you say Kneber and Neb or Neber actually, in 2002 reproduced this result again, the performance simulation with two mass ratios, and observed the same phenomena. Their conclusion was a little more optimistic in the sense that they say, yes, we do observe collisionality, but it's not enough to affect the density profile, but they still observed such collisionality in their codes. So I think from this test and from the way codes have been tested in the 80s, we can extract a really interesting methodology that could either replace or at least supplement what's currently done in astrophysics, the methodology of what I call crucial simulations. I characterize this methodology through 5 steps. So first we select a property P seemingly predicted by simulation with dubious physical significance. So it can be the density profile leading to the Casper problem, it can be the number of subhalos you're observing, it can be the spurious fragmentation. Step 2 is to list all the possible physical mechanisms and numerical artifacts that could generate this property, and then design a simplified scenario where all these culprits can be ignored, but one on each side, so that you really have an alternative between a single physical hypothesis versus a single numerical hypothesis. Then you find a feature, a property, a prediction that is implied by, untold by one of the hypotheses, the physical or the numerical one, and you run a simulation to verify whether this feature holds in the simplified scenario you've designed. So I think this methodology can do really well in diagnosing artifacts. It's not going to tell you whether your simulation is fully reliable or not, but it's going to tell you whether it suffers from artifacts or not, and whether you can trust a specific parameterization you chose. One of the problems with this methodology, given the current framework and the current sociology of the field is that clearly they're not realistic at all. You're not going to produce beautiful galaxy, the beautiful galaxy you can see right now produced by different groups which are trying to reproduce the galaxy we observe in the local group, for instance. And so you're not going to reproduce realistic galaxies like this, but you can learn a lot from your codes, and you can actually get back a sense of modularity by understanding better which component of your simulations are responsible for what. So I think even though it's going against the trend somewhat, you can learn a lot from crucial simulation, and they're so simple that they're not going to jeopardize the computational time that is allotted to you. So there are several advantages with this methodology. So in conclusion, convergence studies and code comparison are unable to detect artifacts generated by discreteness-driven effects. And I think I provided some theoretical consideration to explain why I think that convergence studies would not be able to detect discreteness-driven effects. But I think it's also clear that they fail in doing so when applied to the spurious fragmentation case. So if convergence study and code comparison fail when it comes to discreteness-driven effects, why should we trust them at all? And why should we base our assessment of n-body simulation only based on these two methodologies? Especially given that discreteness is one of the main sources of artifacts in n-body simulations. In the 80s, some astrophysicists, I've mentioned a few, Epstein and Eastwood, but also Mellott and Chandarain, have been appealing to what philosophers would call crucial simulation to test their codes or test the presence of discreteness effects. So they've been opposing numerical hypotheses to physical hypotheses in order to detect discreteness effects such as collisionality or two-body scattering effect. So I suggest to generalize these examples such as to provide the grounds for a new methodology for assessing whether n-body simulation faithfully track the logical consequences of the cold dark matter model.
Thank you very much. Any question? Right, maybe I can start. I think the presentation made me think about, I think it's an expression from Winsberg, that he says that in ways simulations have a life of their own because they are modeling.
Yeah.
So, would you be okay if I describe your view as a way to experiment on computer simulations to try to discover how they work and to try to get a better understanding of the properties and how they could give us insight about some target systems or not? Is it okay to see things like this?
Yeah, I think that crucial simulations are mainly, not necessarily only, but mainly a tool for understanding better simulations themselves, like understanding better what is the role of different components and what is the possible interplay between them, and getting back. Winsberg is also focusing on the lack of modularity of current simulation and why it's really difficult to evaluate the success or failure of this simulation because we don't know which component is responsible for their failure and success. So mainly crucial simulations are a way to explore simulations themselves and to better understand them. But you can also understand better some physical mechanism by using crucial simulation. Like tidal stripping that we mentioned earlier, like it's a really difficult mechanism to describe using only analytical tools. But if you run a simulation, as Frank van den Bosch did, that tests whether physical disruption is either due to tidal stripping or to inadequate force softening, you might get a better understanding of tidal stripping too. Still, I think the crucial simulations are really focusing on simulations themselves and better understanding simulation as opposed to better understanding the world, that's for sure, yeah.
So in a way, this idea of modularity, it's like, we don't really need to look at the code and understand how the computer simulation works because we put a lot of things by hand to make it work. So the idea is to now we try to experiment on it to get an understanding of what's dependent on what in the results we get.
Well, the motto of classic typical verification and validation procedures for simulation in other areas like engineering, for instance, is based on modularity. The idea is that you can evaluate the impact of a component locally. You can assess whether a component is well calibrated locally and then take care of another component and then take care of another component and so on and so on and so on. And so you can build up a way to validate and verify your simulation by building up from these different pieces. Clearly this is not doable with simulation according to Winsbergian climate science, but I think it's the same in astrophysics, because when you're introducing kludges or tricks like force softening is really a departure of Newtonian physics. So when you're implementing a kludge like this and you see that maybe your simulation is good at reproducing the phenomenology, you don't know whether the numerical scheme you're using or the physics you implemented is responsible for this success, because you have already blurred the line so much between different components that you don't know to attribute the success or failure of your simulation.
Yes,
so you described crucial experimental simulations that was used to design whether a certain simulation was collisionness or not. But the main problem with the simulation we are interested in is the question of whether the way they discretize dark matter is responsible for this or for that effect.
Yeah.
So it seems the rational question is there some hope, is there an idea of what sort of crucial simulation could tell whether the way dark matter is discretized is responsible for this effect?
There was hope before the study by Power et al. Published in 2016, because they thought that discreteness effects were mainly caused by small-scale velocity fluctuation, and so they thought by better understanding force softening, you might not have the physics exactly right, but you're going to get rid of these discreteness effects of most of them. But as I'll go back to this. As these convergence studies show, increasing the force softening here didn't have any effect on the mass function of the mass function for halos. So there's two ways to understand that. One is that maybe you have low mass halos in CDM simulation, but there are so few of them that real halos dominate and they do not affect the mass function. But you can also think that the discreteness-driven effects are not happening at small scale, and they might be due to large-scale fluctuation, what's called collective relaxation. And if that's the case, then calibrating better your force softening will not wash out these discreteness effects, and that's one of the paths that are currently explored. And I think it's a really interesting path to explore, because there was a paper by Weinberg in 1993 showing that astrophysicists and astronomers have been mainly focusing on local relaxation, so summing over two-body scattering to calculate two-body relaxation, but not on collective relaxation. And according to him, collective relaxation will dominate by 100 times what's happening at local scale. So if local relaxation is already big enough that the system is losing entirely the memory of the initial condition and initial velocity, and it's nothing compared to collective relaxation, then we really need to worry about collective relaxation effect. And it's really interesting to see that here the mass function is not sensitive to a change in force softening, and that would be the case if relaxation is due to collective effect. So that might be one path to explore, but if that's the case, then the hope right now is it's not clear how you would remove collective relaxation from a simulation. Force softening is not going to do the trick, so it's not clear right now how you can get rid of these effects, if that's the case. Yeah.
So I have a series of questions about the idea of crucial simulations. Maybe it would be useful to go back to the slide where you characterize the steps that one is supposed to take. So step one seems maybe the only step where I don't have a question. So you select, whether they're collisional or not, something like that. You're interested in figuring out what the physical significance of this really is. Now, in the second step, you need to come up with a list of all possible physical mechanisms and all possible numerical artifacts. That, to me, first of all, it suggests that there are the same number of physical mechanisms as there are of numerical artifacts in the way you
Well, not necessarily.
That seems perfectly contingent.
Yeah.
Right, okay, good. Now, is it realistic to come up with a list of all possible physical mechanisms and numerical artifacts that could generate that?
That's a really good question. So when it comes to collision and the plane symmetric collapse that I've been talking about, the good thing is that there's no physical mechanism you need to worry about, right? The system is supposed to be collisionless. So either you observe the prediction you extracted from collisionality or nothing happens. So sometimes you don't even have to worry about physical mechanism. In other situations, I've been mentioning the missing satellite problem before, and the fact that the missing satellite problem is mainly due to disruption, matter disruption, and what we don't know whether matter disruption is has a physical source or an artificial source. In that case, there's not so many explanations available to explain what kind of physical mechanism could explain why a system dislocates and why a subhalo would dislocate. In the crucial simulation by Van den Bosch I mentioned is listing 3 of them: tidal stripping, tidal heating, harassment. And if you want to be sure that you're exploring an alternative between two systems, you need to make sure that you only have one physical mechanism at play, again, one artificial mechanism. In that case, it was possible to not only exhaustively list the physical mechanism, but also to design a scenario where you could only focus on one of them. I think in many cases it's going to be the case. It doesn't mean that in all cases you have such a good understanding of what's happening that you can actually provide such a list. So there's cases, I think, where crucial simulation either are not possible or we need to learn way more about systems before being in a position to apply them. But when it comes to like the cases I've been mentioning that of collisionality, for instance, you have really easy way to detect whether there's collisionality in the system. I mentioned a few of them: mass segregation effect, plane symmetric collapse, but you also have an interesting experiment by Boscheff showing that if you simulate an isolated halo that is supposed to be fully stationary and tracking the variation in the integrals of motion, in the constant of motion, if your halo is stationary, they shouldn't vary. They should be a constant of motion. So if you observe variation in them, you have collisionality in your system. So in all of these cases, they could list all the physical mechanisms at play and design a scenario where they could eliminate this mechanism. It doesn't mean that it's going to happen in all the cases, but I think it's a necessary step.
Right, those 2 is definitely a necessary step, because I don't see how you have any chance of doing 3 if you're not really confident that you know all the possible ways in which this could physically or artificially be generated. Now, I'm not sure I understand step 3. So if you say, for instance, you're interested in a property that couldn't be produced by the physical mechanism, how can you have a simplified scenario where somehow there would still be one physical mechanism of producing it? I mean, I don't quite understand that.
So it's true that it's trickier with the numerical part than with the physical part. I think that listing the physical mechanism at play and finding a scenario to get rid of them, it's doable, not necessarily always, but it's doable. when it comes to numerical explanation, what has been done so far is to, so imagine that your suspicion is that inadequate force softening is creating matter disruption, for instance. Let's focus on force softening. So you think that parameters such as the time step, the force accuracy, the mass resolution do not play a role in this, in generating this property that you're doubting. What they started by doing, and by this I mean Van den Bosch or Bochet, or people who use this kind of reasoning so far, what they started by doing is to run simulation varying these parameters, so mass resolution, forces that they didn't think had an impact, with all of the other parameters fixed, checking the impact of this specific parameter, and then choosing for this parameter, and it's getting a bit technical here, I'm sorry, but checking for, choosing for this parameter the most conservative value they could find. And by this I mean, if beyond some value you don't have any difference in the accuracy of your simulation, you don't have any observed difference in the prediction you're making through your simulation, but only using more computational power, then you're gonna choose the value at which you observe no change in the variation. So they did that for every single numerical parameter, and then they kept this value that they call fiducial values fixed for all of the other simulations they ran varying the force softening. I think it's not fully satisfactory, and I think it's difficult to say from this kind of reasoning that really you have excluded other possible sources of artifacts, but that's the beginning of the reasoning. I think you can do better than that, but it's what has been done so far, like having fiducial values for all of the other parameters that could generate artifacts.
Okay, but what happens in those situations of which there are cases like the collisionality problem, where there is no PI, so the PIs are an empty set? There's no physical mechanism that will generate that. So how are you going to be able to get to the disjunction in step 3?
Well, then
it's just NI.
Yeah. Then either you observe E or you don't observe E. Like
now,
either you observe the one-dimensional system to thicken or you don't.
So you
in the plane symmetric collapse
to
case.
step 4 then, you say that if under whatever physical mechanism there is, because there is none, you should see such and such behavior, but there's something that couldn't, under any assumptions of the physics, be produced but by this particular numerical factor that was causally responsible. Okay, now what you do to determine whether or not E shows up is you run a simulation.
Wait, yeah.
Right? So, isn't it guaranteed that you're going to get, the NI bit? Because you're...
Well, if a code is collisionless and is actually successful in being collisionless, then you wouldn't observe the plane to thicken, for instance. You'll have the system would remain one-dimensional, so you wouldn't observe the feature E corresponding to the NI in that case.
Simulation.
Yeah.
Okay, I see.
But you're pinning down exactly the difficulty with this method, and I think it's just like capturing a rough framework. I'm trying to capture what has been done in the 80s, but I think there's a lot of work to do, especially on the steps and excluding. I think physical mechanism, I'm not too worried about it, but a way to really make sure you exclude different sources of numerical artifacts, that's really tricky, because from the beginning you've been assuming that you have a lack of modularity and you don't know what component is responsible for what. So yeah.
It could be that you miss one numerical artifact or one numerical factor that screws up the simulation, and then you think you've isolated one now, and you make this simplified simulation, and maybe you find that it's, you find not E because you've controlled for Ni, for that particular factor you identified. But you forgot about the hidden factor, which also produces the thing. And then, this is completely useless. So it really depends on step 2, crucial.
Yeah, I fully agree with that, especially on the second part of step 2. I'm not too worried about the first part, but step 2, like, would it be enough, for instance, to test all Ni against the P you've selected, for instance? Would that be enough? I'm not sure. So, but maybe by running more and more crucial simulation, you will understand more and more what component is responsible for what, and then go back to the beginning and improve your methodology. I don't know yet, and I clearly need to flesh out this part. It's really meant to capture what physicists have been doing in the 80s, but there's a lot of work to do in order to justify all these steps. Yeah, fully agree with that.
Just a figure on this. Oh. So do you think there is so when you say all the step 2, you say all the possible numerical artifacts?
All the possible numerical sources of artifacts, yeah.
So you think it's a finite list? I mean, because it's epistemic possibilities, right? We don't really know. The other thing, is it possible, even in principle, to find all the possible sources of
there's a finite number of components, and this component might interact or not. You don't know how they will interact. But you might have a very, very large number of Ni for sure, but an infinite number of them, I don't see why.
It's independent sources, but because I was thinking you can also think about the interactions between the maybe there's 2 artifacts interacting and generating a third.
Yeah.
So but then if you start considering interactions, so
that's another problem. You can have artifacts compensating each other toward the correct solution, for instance. And if that's the case, do you want to say that your simulation is reliable when you don't know what's happening in there that is responsible for the success? Yeah,
it's probably sometimes the case where the simulation works because the artifacts are compensating each other.
Yeah, it's probably the case.
So over the last few weeks, we've been discussing the epistemology of computer simulations and whether they're better characterized as logical derivations with fantastical computing ability, or whether they're experiments in their own right. And while towards the end we seem to agree there's some sort of combination, just to address the purists out there who want them to be one or the other, I wanted to pose a question to you about your opinion with this setup that I'm about to give you. So Wendy Parker, who wants to say they're experiments in their own right, rhetorically poses questions that someone of the opposite camp would need to answer, to say that simulations are experiments on abstract mathematical systems. So the first question is, how does an intervention on an abstract system take place? And so to me, it seems obvious. You change the initial conditions and you vary the parameters. That's how you intervene on the system. And then how does that abstract system move through a series of states? And again, to me, the answer seems obvious. The algorithm specifies what the succession of states looks like, and we actually, have a readout of that. And based on the examples you gave of just having these various models and checking them against astronomical observations, robustness analysis, as well as crucial simulations, to me these all seem like examples of how you could experiment on mathematical systems. So I was wondering, one, if you agree with that, and two, where you lie in this debate, especially with respect to cosmology.
I think it's a really, really tricky question, because I think the answer can only be found if you already decide on how similar your target system and the outcome of a simulation are. In order to conceive a simulation as an experiment for me, like something playing the role of an experiment, you already need to think, I think, to my eyes, that the outcome of a simulation is so similar in every relevant respect to your target system that it's actually playing the role of the experiment, that is telling you, informing you about the system. So I think you already need to decide on this before being able to decide on whether it's an experiment or not. And this is exactly the question I'm interested in. Is that the case? Is the outcome of the simulation actually, can it actually be matched to the real system? So I'm like one step away from answering this question, because I just don't know if right now from simulation in astrophysics we can really learn anything from real systems.
Okay.
So far I think it's too early. Right now I think it's too early to say that what they are simulating is matching real target system. And if that's not the case, if we cannot decide that, I don't think we can decide on whether they play the role of an experiment or not.
So do you think we can still say we're experimenting on abstract mathematical systems?
I think the crucial simulation are a way to experiment on simulation for me. I think it's the right way to put it. In the robustness analysis you mentioned before and observation matching too, it's really helping you understanding simulations better, but does it mean we're understanding the world better? That we don't know until we find a good methodology to determine when the outcome of a simulation is trustworthy or not.
Right.
Yeah.
Thank you.
May I follow up? You said a couple of times that computer simulation can be realistic. This implies that they can be...
They can aim at being realistic. Like, they aim very often, they aim at providing this kind of picture that is reproducing the... So here it's the galaxy Romeo, it's a simulation, and it's reproducing one of the galaxies you can observe in the local group. So if you put the images apart, close to each other, it's really difficult to tell them apart. And for them, it's a sign of like the great success of the simulation. That's what I mean by aiming at reproducing realistic galaxies.
Because I was thinking, it makes perfect sense to me say that computer simulation might be realistic or not. Doesn't seem the same for experiment though. Saying that an experiment is unrealistic would say that you're not really making an experiment, because when you do an experiment in classical laboratory, you're dealing with real stuff, right? So, what do you think about, that seems to be a kind of objection to the view that computer simulation might be experiment. I don't know if it's a good objection. What do you think?
Well, real experiments in some sense are more realistic than our theories, right? Theories are based on idealization. If you want to experiment on thermodynamics, you have like ideal gases on one side and real system on the other side. So in some sense, experiments are more realistic than prediction of your theory. When it comes to but can you talk about a non-realistic experiment? I don't know. You can talk about a bad experiment in that it doesn't capture what it wants to capture about the world, but an unrealistic experiment, I don't know. But clearly, yeah, in simulation you can choose whether you want to simulate you want to approximate a real system, something you could possibly observe in an astrophysical system, or simulate something that clearly will never be observed and never existed. You can do that, like an isolated sub-hello, as is the case in Frank Delbosch simulation. You don't have an isolated sub-hello in a real system that doesn't exist. I'm not sure I answered your question, but I'm still thinking about what it would mean to have an unrealistic experiment.
Yeah.
I'm not
that
sure.
was the point.
Yeah.
It seems
Yeah.
doesn't make sense. And the inference was, well, then computer simulation cannot be experiment, right? Because
Yeah.
one of them you can use an adjective.
I will need to think about that further, I think.
I have another question about crucial simulations. In step 4, when we're trying to identify a feature E and then determine these two conditionals, that requires that we're able to somehow determine in physical situation characterized by PI whether or not there will be that effect E showing up or not. Now in some cases that might be perfectly unproblematic. We can determine that relatively quickly without having to actually sort of derive things step by step. But I'm worried that there might be situations where this is not possible because the physical system is, after all, too complicated. We may not be compute anything, which is why we do, or not much anyway, which is why we do the simulation in the first place.
Yeah.
So it would have to be some sort of feature which is evident in the physical system without much computation, perhaps.
Yeah, I fully agree with everything you said, and I've already been very worried about that point, so I already talked about what could possibly be done to make sure you actually can find a feature E. And one thing I've been thinking of, and I think can be efficient in doing so, is actually redirecting the use of code comparison. A code comparison like Aquila that was done in 2012 based on comparing simulations with their favorite calibration and their favorite state-of-the-art subgrid physics was disastrous in their conclusion because they didn't find any robust properties and they didn't succeed in simulating any realistic properties. But they gained a lot of knowledge about real physical system, and they gained this knowledge thanks to the specific methodologies they had, which is, I don't know whether I can write, but so they had, like they only, I think if I remember well, they only compared 3 different codes, Gadget, so the Gadget 3 version, RAPSES, and RFO. So you have 3 different kind of gravity solver, but you had 2 versions of RAMSES and 6, I think, version of Gadget 3. So for all of these versions, you would have the same gravity solver, but when it comes to the subgrid physics, they all had their favorite implementation, like say this one had supernovae, this one had black holes, this one had black holes and cosmic rays or something like this. So what was interesting is that you had an overlap between different modules. So for instance, if you compare a repo I'm not talking about the cooling and the other parameter, but let's focus on the feedback prescription, for instance. If you have a repo and Gadget 3, the version that implement black holes and cosmic ray, and they implement the subgrid physics exactly the same way. So let's say that this version of Gadget implement black holes feedback, cosmic rays feedback, and they implement them exactly the same way. But they have different gravity solvers. Then if those 2 codes agree, it's more likely that it comes from the physics than from the gravity solver. But if these 2 codes, if 2 versions of Gadget 3, which have the same gravity solver but different subgrid physics, disagree, then again you can make the same kind of reasoning. So if you have an interesting overlap between different modules, you can actually draw some preliminary conclusion about what's responsible for what. So for instance, if I remember well, there was a agreement between REPO and one version of Gadget 3 on the stellar formation rate. And they concluded from that the subgrid physics was more likely responsible for the agreement than the gravity solver, because gravity solvers differ. And they both had late induced stellar formation rate. And so in that case, they could actually draw the conclusion that the morphology of the galaxy is due to the subgrid physics, and in particular to the stellar formation rate as it was implemented in these 2 codes. So if you're constructing a code comparison with such an overlap between different models, you could have some insight about a possible agreement or disagreement between different modules and use that as a way to test your code. It's still it's not You cannot draw as a conclusion from that it is absolutely certain that the sacred physics is responsible for the agreement, but it provides you some insight into what might be the case or not. And I think it can supplement crucial simulation in an interesting way.
Yeah. So that seems a very good methodology that I can easily follow with code comparisons by trying to vary just one bit and see what it does. But I'm not sure it's fully captured by the steps of the crucial simulation there. It seems to me what you're doing is something slightly different. What you're doing now is to compare two or maybe more than two possibly codes, and with small variations, small differences, and so that they will lead to different outcomes. And then you somehow compare that to what you would expect rationally from your independent understanding or intuitions about the physics.
So
whether they give you sort of the correct output or not.
So it's not captured at all by the 5 steps. It's, for me, a way to think, well, in some case it's really easy to determine the feature E that you would observe. In some case it's really complicated, and the more we learn about the system, the more tricky it's going to be, the trickier it's going to become to find a feature E. So it's trying to find a source, a new source of hypothesis to test. And I think code comparison, they're extremely expensive, it's extremely time consuming, so redirecting them in such a way as to provide hypotheses to test for crucial simulation will ensure that whether you have agreement or not among codes, you will learn a lot about what's responsible for what in CDM simulations.
But isn't there then a tension between step 4 and step 2? In the sense that, okay, it's not captured by this, but cases where you can find something looking like step 4 are cases where step 2 doesn't work in the sense that it's opaque, because if you don't have access to the
so what's opaque is not, so you have a first difficulty here that is making sure you have an exhaustive list of physical mechanism, an exhaustive list of numerical artifacts, and that you can exclude them. This is another difficulty. The opacity here is to find if the numerical artifact here is really responsible for the property, what kind of prediction can I make that would that can be extracted from this numerical artifact, and that it's not clearly it's not clear that it's always be the case that it.
But what I was trying to, maybe I'm wrong, it's just I'm trying to understand, but my feeling was that in order to resolve the problem of step 4, you have to consider cases which are inconsistent with step 2.
So there are two separate things. You will.
So, but because you were considering
Code comparison,
but
like imagine that. So this project actually has been run in 2012. They made this conclusion saying we didn't find any robust property, but we learned something about our system. It's like system with a specific stellar formation rate do better at reproducing the morphology of galaxy we observe, for instance, a disk galaxy or whatever. This was done in 2012. Today I could say, maybe you can test that in a crucial simulation. Maybe I can test whether it's true or not that this specific component, the stellar formation rate, will have an impact on the morphology of the galaxy, and design a scenario where I can actually investigate this hypothesis vs a numerical hypothesis. So those are two independent processes. You could use the code comparison constructed that way as a bank of data, as a resource that doesn't necessarily enter the reasoning that you have here, unless I misunderstand the question.
I'm not sure.
It is true that if it's that complicated to find what's the physical mechanism responsible for the morphology of galaxy, for instance, then yeah, it's going to be difficult to come with a list of physical mechanisms here to explore. That's true. But whether it's contradictory or not.
When you were talking about code comparison, I understood that as a way to bypass the difficulty of step 2.
It's to bypass the difficulty of step 4. provide numerical, physical and numerical hypotheses to test. But as you can see, like there's a lot of work to be done in this area. So if you're interested in the topic, just run and join the move.
Do you have any other question?
I do.
And maybe I have a last question about to understand the difference between cold dark matter and warm dark matter. So you said that one difference was that one was bottom up and the other top down in the generation of structures.
Yeah.
So what's the intuitive way to understand this? So basically we have different scales bring out the generation of structures because so the warm dark matter was the particles are moving faster or something, and so
Yeah, they have a higher thermal
so
velocity.
it
Thermal
prevents
velocity.
structures to be triggered the smaller scales because the motion of the particles prevent structuration through gravitational. Is it what's going on?
The fact that they have a higher thermal velocity is washing out small scale fluctuation. The effect of small scale fluctuation is disappearing because of the thermal velocity.
So it means that we
So you have a cutoff in the power spectrum. In the cold dark matter model, you have power at all scale, but in warm dark matter model, you don't have power below a certain cutoff corresponding to this thermal velocity.
Okay. Last question.